Good morning, everyone. My name is Kyle Buckheit. I'm a PhD student at the Missouri University of Science and Technology, and this summer I worked with Dirk van Essendelft, and today I'd like to speak to you a little bit about combustion kinetics modeling and validation for use in multi-phase computational fluid dynamics. So first I'm going to give you an introduction on what the C3M program is that I used and how C3M exports into CFD code. I'll go into some bug finding I did, and a little bit of the MFIX validation of the gasification data I had, as well as some conclusions in future work. Okay, so first, what is C3M? C3M is a computer program being developed by my mentor and his group, which stands for Carbonaceous Chemistry for Computational Modeling. So what does C3M do? It can perform virtual kinetic experiments using various operating conditions and fuels to generate kinetic rate expressions for particularly combustion type of reactions. So once you perform that experiment, you can actually export the kinetics into different multi-phase CFD programs, such as NETL's MFIX, ANSYS's Fluent, and CPFD's Barracuda. So whenever you first run C3M, what you need to do is select a fuel. There are predefined fuels already built in, but you can also define your own fuel based on the proximate and ultimate analysis. You then select a chemistry submodel such as gasification or pyrolysis, and then you select a kinetics package that tries to model the chemistry you have selected. And then finally you set up the conditions such as the temperature, heating rate, gas composition, so on, and you can also see a preview of the equations below. And then you just run the experiment. Whenever you're ready to export, you again select the fuel type that you used, select the chemistry model again, select the kinetic package again, and then select your conditions. Now here you can see little checkboxes next to your conditions. What you can actually do is export more than one condition at the same time. So say you want to export gasification alongside pyrolysis or something like that, you can actually select gasification first, go back, select your other reactions, and then run that as well. And then whenever you're ready for export, you select the drop-down box and you can see the options for MFIX, Fluent, Barracuda, or just exporting a simple report. Here's a sample of a report that you can export. You'll see that it contains the chemical rate expressions, as well as information on the chemical species, such as the molecular weight, heat of formation, heat capacity, and so on for all the chemicals related to the reaction. And here's a sample Fluent export. The first, you'll notice that it's written in the C programming language, and it also utilizes various macros that Fluent understands to pass information back and forth from the Fluent solver to the UDF in order to calculate. And here's a sample MFIX output. It's written in the Fortran programming language. It also outputs multiple files. One of the files is the mfix.dat file, and it contains the chemical stoichiometry for the reaction and the chemistry information for the species. Another notable file is the user rates file. It contains the actual kinetic rate expression. So C3M is a nice little program, but what did I do this summer? Well, since it's in development by my mentor's team, I got to bug check the program. So I had to go through and create sample conditions for the various chemistry models and kinetics models, export them, and make sure they would work in their respective program. For example, like if I export a Fluent UDF, I had to make sure it exported correctly, the report was okay with it, and it would compile inside of Fluent and run. So sometimes the Fluent UDF was incorrect, sometimes the MFIX output was incorrect. Sometimes those were actually both okay, and the documentation that comes with the software was incorrect, so I had to go back and compare it to actual theory to make sure everything was compatible. All right, so after I did that, I could do a little bit of validation work. Inside of C3M, there's a built-in MFIX validation program. In order to use this, you just have to select the export folder where you first exported the C3M MFIX data. And you can also match different conditions in order to get your conditions right to run MFIX. For example, you can change the gas species mass fractions, You can change the temperature profile, which also sets the time of the experiment, and you can modify other simulation variables such as the time step that MFIX will take, mass flow rate, and things like that. All right, here's a little bit more information about the gasification experiment and the model I used to mimic the experiment. So first, the gasification experiment used PRB coal, but it only used the char, so it only used the fixed carbon portion of the actual coal. It would run 0.2 grams in a drop tube type experiment. To try to model that, we used gasification chemistry using PC Colab type kinetics, and we used the TGA form of the MFIX validation. And here are some results. For this particular gas, 425, we're at 975 degrees C, and we're feeding in 10 mole % carbon dioxide, and the rest are inerts. So we're only looking at CO2 gasification for this case. Now, since the concentration is a little bit low, the model curve is the blue curve, and the experimental data is the red curve. So the model underpredicts the conversion of the experiment. But if we go to the next gas, we're running at 30 mole % CO2 as opposed to 10 mole %, and this time the model data more closely matches the experimental conversion. But then if we go to 50 mole %, we have a better match at the later part of the curve, but we're still over-predicting at the earlier parts. We also did some steam gasification runs. So here's a 5 mole % of steam. Now this has the opposite problem where we're over-predicting the conversion rather than under-predicting. And with 15 mole %, the curves are very close. But then whenever we go to 30 mole %, we're over-predicting more again. It's possible that because the steam gasification runs are more, the reaction rate for the steam gasification is higher, so it's possible that the time step used for the MFIX run needs to be controlled a little bit tighter in order to get a closer match. All right. So in conclusion, C3M is a nice program that can take multiple inputs of different kinetic information and export them in ready-to-use format for different CFD codes. It also has built-in testing, so you can just validate your chemistry before you try to run a full CFD simulation. Also, because of the work I did this summer, the group was ready to get, or the group was able to get ready for a stable release of the program. And they actually updated it on Monday. So for future work, the group is trying to implement what they're calling a surrogate model, where instead of taking just one input, as I had done before, they're going to take a range of inputs, such as a range of temperatures, range of compositions, and create a model surface for the CFD code to interact with. Because in a CFD simulation, it's possible that in different sections of the domain that the temperature or the gas composition vary quite a bit. So one fixed kinetic rate may not be accurate enough to actually match the experiment. So using a range of inputs, you can actually get a range of kinetic rates to pull from in order to hopefully get a more accurate result. All right, so I would like to thank my mentor again, Dirk Van Essendelft, and his group. It was great working with them this summer, and I would like to thank the Mickey Leyland program for giving me the opportunity to work with them. And last but not least, I would like to thank my wife, Jing, for encouraging me to do things that I may not have otherwise done. So thank you. And did we figure out why that light's flashing?
I have some very important technical advice for you. I've been married for 40 years, and I found that it's helpful to acknowledge your wife in the beginning. No, seriously, good job.
Any other questions?
Just checking, everyone else sees the flashing light?
Yeah.
That was a little distracting.
It
Yeah.
does, you know, that. There's a what's running a check, and some of you guys see it. There we go. No need to be concerned.
Okay.
So my name's Luis Gutierrez, and my mentor was Dave Tucker, and I worked at the Hyper facility in the Morgantown site. And this is my second year working there, so I was pretty familiar with the site. And basically, just to kind of give you a small intro on the Hyper facility, and Conrad later on today is going to give a better overview of the Hyper facility. But basically what it is, it's a hybrid system. And a hybrid system, the goal of a hybrid system is basically to couple two technologies in order to increase efficiency. So in this case, we're coupling a gas turbine system with a solid oxide fuel cell emulator, where the heat from the solid oxide fuel cell simulator actually provides power for the gas turbine, so it kind of has this cycle where it's efficient. And everybody agrees that these systems are really, really efficient in theory, but in practice, they're really, really hard to control. And so that's kind of the area that I was working on. How can we control these systems? And so one really small subset of this problem is data noise propagation. And so throughout the system, throughout the gas turbine, there's dozens and dozens of sensors. And these sensors are responsible for monitoring and also feeding in acting as an input to a controller in order to regulate fuel valves. So if you can see here on this corner right there, the sensors kind of feed into the controller, and then the controller feeds into the fuel valve, which gives fuel to the gas turbine, which controls the sensor. So it's kind of a cycle. So the speed gives the controller a mark for the controller to give the gas turbine to regulate the fuel, and it goes around. So a really unstable signal in this would cause, one, a misallocation of fuel, so you're wasting fuel, and two, it's stress on the system for it to be very, very volatile. So noise reduction in data series and in different forms of data is pretty heavily researched, and there are a lot of methods to do it, and a lot of really good methods to do it. But most of the really good methods are nonlinear. So by nonlinear, we mean is they take a really long time to run. And here, if you can see right here, this method here is really good. As you can see, it approximates the curve really well, but it introduces a phase lag there. And this phase lag actually, this could be detrimental to the system and actually cause the system stall in time and destroy the turbine, cost thousands of dollars, tens of thousands of dollars in damage. So, and the alternative is these linear methods were a little faster, but sometimes linear methods don't work so well, and when there's a trend in the data like this one, they don't really capture them very well. So it's kind of, the idea was, can we find something that runs really, really fast, but that also can capture the trends in the data? So I don't have an engineering background. I'm computer science, and most of my work was in big data and data mining. So when I came into this, I just tried to use the tools that I had at the particular time. And so one of the tools that I had was, smoothing data in time series, what you do for like financial data in order to predict where the market's going to go. So I thought like, well, why don't we try exponential smoothing? And so in this system, basically, you have 3 sensors on the turbine, right? And the idea of exponential smoothing is just a geometric series. So all it is, if you expand this right here, you can expand it to the geometric series, where S equals the smoothed observation, Y the raw signal. And the only difference between this and the geometric series is that this smoothing constant, this alpha value, acts as a way to truncate the series. So at a certain point, in the geometric series, we're weighting. So older values are weighted less than newer values. But at a certain point, we're going to say, oh, we're going to cut off, and we don't care what happened 10 or 12 values ago. So that's what this alpha value does. And that's single exponential smoothing. We also worked with double exponential smoothing. And double exponential smoothing is pretty much the same thing. This first equation is equivalent to the other one, but there's an additional equation to account for the trend. So we tried this, and this is all happening in real time, so we wanted to act really, really fast. So these are some of the results we had. As you can see, the yellow represents the raw signal, the blue is the single exponential smoothing, and the red double exponential smoothing. And they both represent a huge reduction in noise. The only problem is, if you notice, is that the blue undershoots the transient a little bit, and the red kind of overshoots a little bit. And that's not such a big deal in speed because we're dealing with a large range, but later I'm going to talk about airflow, and that's going to be a much bigger deal. So here are just some results that we had. So we said we wanted to regulate fuel. So on your right-hand side here, here's the speed, and here's how the speed's reacting, and here's how the fuel valves are reacting, fully coupled with the speed in real time. So this is just the average of all three sensors. This is status quo, what they currently do at the hypersystem, and this is how the fuel is. You can see the fuel's really, really noisy. It's an unnecessary wear on the turbine. And here's single and double exponential smoothing. So this is single exponential smoothing, how the speed's acting, and this is how it kind of regulates the fuel. You can see it's a lot smoother right here. It's a little noisy at the beginning, but then it kind of converges and starts to smooth out. Double is smooth pretty much all the way, and you can see that it significantly decreases the noise. And actually, the numbers are, in single exponential smoothing, there's a 45% reduction in noise. Double exponential smoothing was an 84% reduction in noise. There was no detectable phase lag, which means that it was all happening in real time. It was a linear time algorithm. We were able to publish these results and have them presented in Germany for the ASB Turbo Expo. I didn't present them. My lab mate did. Maybe on my exit survey I'll say that Mika Leland should have sent me to Germany to present these results. But there's still the problem of overshooting and undershooting the transient. And so that's not as important on speed, but on airflow it's really, really important. We want to capture. And this is actually, very, very detrimental to the system if we don't capture the transient on airflow. So here's an example of the same algorithm on airflow, and as you can see, there's actually introduces a little bit of a lag, and you can see this doesn't quite go all the way up and doesn't quite go all the way down. And so this is a really big problem. So then my mentor was like, well, good job, you published the paper and everything, but what about this problem? So can you take care of this? Can you somehow make a linear time algorithm work as well as a nonlinear algorithm and produce the results that we want? So before I start, and I think if there's anything you could take from this presentation, I want you to take this part from it. We need to do a noise analysis to really understand what's going on in the system. And so for me, like, probability and statistics, I always reduce it down to online poker. And I know this is a little weird, and it sounds like it's a little bit of a stretch. And the system, like, airflow sensors and a hybrid system sounds like it's completely different than poker, but actually they're exactly the same. So, and so it's a little bit of a stretch, but if you're patient, I can show you how these problems are the same, and actually the solution is the same too. So a while ago, I actually was not making. This was before I was a highly paid Mika Leland intern. I wasn't making enough money to pay rent, and so I started to supplement my income playing online poker. And so if anybody knows about poker, there's a really good chance that there's not a very good chance that you're going to get a really great hand like 4 of a kind. And there's not a really good chance that you're going to get a really bad hand like nothing. But there's a really good chance you're going to get an okay hand, maybe a pair of 7s or something, right? And actually, so maybe you can play 2 or 3 times, and maybe you might get a really good hand and a really bad hand. But the more you play, the more you're going to converge on this mean, right? So the more times you play 10, 20, 30 times, you're going to converge on this pair of 7s. And actually, the system is doing the exact same thing, and the smoothing algorithm is doing the exact same thing. So there might be a time where there's a point that's an extreme outlier and it goes really high, and there's a time when there's a point where it's an extreme outlier and it goes really low, and those kind of represent the transients. So the transients are like a really good hand and a really bad hand. But in general, when you're at a steady state, when the system is going without a transient, when there's no upward or downward trend, then you kind of converge on this pair of 7s, and the algorithm understands that, and at a certain point, it converges on a mean error, and it produces a really, really smooth signal. Right? So then you're asking, well, how did you make, if everybody converges, and first I want to say, also this is all predicated on something called a Martingale process. And so this kind of sounds a little complicated, but it's really simple. What a Martingale process is saying that what happened in the past doesn't affect what's happening in the present and doesn't affect what's happening in the future. And that's a really fundamental law in probability. So just because I had a bad game last time doesn't mean that I'm going to have a bad game this time, and I'm not going to have, I'm going to have a bad hand in the next game, right? So that's why like probability is unbiased. So that's the same thing that governs the smoothing algorithms and governs the noise. The noise basically says the point that came before doesn't affect the point that's happening right now, and it's not going to affect the point that's happening in the future. So then your question is, how did you make money to supplement your rent? If everybody's going to converge on a pair of 7s, how do you make money? then the thing is, like, you actually have to violate this Martingale process. So how do you violate this Martingale process? So the way that I did it in online poker is I used to go into these poker rooms, and I used to find someone who had won 4 or 5 times in a row. So this person's on a hot streak, supposedly, right? But actually, it's just a really, really small sample, and he just happened to get a bunch of really good hands. So what I do is I go in there and I play him, and then I lose 4 or 5 times to him. So I tip probability in his favor. So I play a really, really bad game. So I change the probability, and I violate this Martingale process. So when you violate the Martingale process, now this guy's won 10 games in a row. Now he thinks he's really good, he thinks he's really lucky, and he starts to bet a lot of money. And then I just go back and I play my normal hand. I converge on my 7s. And when I converge on my 7s, we play enough times, I go up, I win 20 bucks, I leave the room and I go find someone else who has won 4 or 5 times, do the exact same thing, do that for a few hours, and by the end of the night, you can pay rent, right? So that actually is the solution to this problem as well. We need to violate this Martingale process in order to account for the transients, in order to account for those small instances where there's a really good hand and a really bad hand. And the way that I did that, and so in this case, so I actually designed a new algorithm, and we're, at the lab, we're pretty excited about this because we haven't really seen anything like this before. And so the way, in this case, so the transients represent a good hand and a bad hand, and this steady state right here represents, just normal, playing for the 7s. So the way that we play a bad hand in noise reduction is we actually let the noise win. We put noise into the system because we know that the raw signal can capture the transient, right? And we know that when we're at steady state, we can smooth pretty good. So what I do is I wrote an algorithm it's a stochastic process, and it predicts a transient, it predicts a change in this data, right? Like right here. And when it predicts that change, it basically says, okay, I'm beat, I'm gonna throw these hands. I'm gonna let noise into the system. Because I know if I let enough noise into the system, I'm gonna cover everything that needs to be covered, and I'm gonna protect the system. As soon as I predict that there's no longer a trend in the data, I start to play my normal hand. I start to converge on those pair of 7s, and you can see here where I'm converging and I'm just smoothing. So that's basically what this algorithm does. And here's some zoomed in results. We did some tests yesterday. I was actually in Morgantown. And you can see here we're capturing the transient completely. We're not overshooting, we're not undershooting. And here in the steady state, there's a few instances where the algorithm gets a little confused and puts in a little bit of noise, but it quickly recovers and converges back to this, to the pair of 7s and plays its good game. And then ultimately, if you look at the system globally, there's an overall noise reduction that's pretty high, and while at the same time we're preserving the transients and protecting the system. So in conclusion, in the beginning of this, we talked about single and double exponential smoothings, and those work really well when you're not so concerned about the transients, but they don't work so well when you are concerned. The noise analysis, we said that when we're in steady state, it's pretty Gaussian. It's easy to converge on an error mean. But when you're not, then it kind of goes out of Gaussian. We're disrupting the system, so it becomes a non-Gaussian. So we got to do something to compete with this non-Gaussian property, and we disrupt this Martingale process by throwing our hands and letting noise into the system. Then designed a new algorithm called a reactive filter. I actually wanted to call it a dirty filter, but everybody was like, that's not professional enough. So we have to call it a reactive filter. And then, we had this initial paper about smoothing techniques in real-time energy systems, which was single and double exponential smoothing. And now we're working on another journal article, which I think will be done pretty soon by next week, where just a comparison of smoothing techniques in real-time embedded systems, and submitted an abstract for the reactive filter for the ASME 2015 Turbo Expo. So thanks to Mickey Leland, we were able to get 4 publications out of all this. And I want to thank my mentor, Dave Tucker, because when I told him this idea that I wanted to insert noise into the system in order to smooth it out, he said I was crazy. And so I worked really hard in spite of him, and to hand him his public defeat. And he's not here today. He's out of town, so he can't accept his public defeat, but I hope that he watches this later to see that he was wrong and I was right. So are there any questions? No questions? All right.
I think you started your presentation by noting that I think you said that you were not an engineer, you were a programmer.
Yeah.
So you would just bring in programming experiences,
Again, math,
other
yeah.
areas that have to this problem. Do you think the fact that you were not an engineer and had a kind of a different mindset about this helped you in bringing this solution to this problem?
Yeah, absolutely. And I think that I guess I'll have to give credit to my mentor for this, because he's usually pretty good at having a multidisciplinary team with him. And so yeah, I think that a lot of there was a controls professor that I was working with, and he was constantly pushing on me the Kalman filter. And Kalman filter is basically standard in the industry for signal processing. But the thing with the Kalman filter is that it was too computationally costly, and I was able to show mathematically that if the Kalman filter requires so much information about the system that at a certain point we already know what the noise is once we have enough information with the system. So I think that, yeah, part of it is that I was ignorant a lot of the standardized ways of doing noise reduction, and I kind of brought in some new tools. And yeah, I think that kind of having a fresh set of eyes in these problems helps out immensely.
Thank you.
Any other questions? All right, thank you.
Hi, everyone. My name is George Adesanya, and I was a Mickey Leland intern at NTL Pittsburgh this summer. I was working in the benefits division with my mentor, Jose Benitez, on NEMS programming and development, and my project was to forecast oil and gas in certain parts of the U.S. I'm a Yale senior studying econ and geology, so this project was pretty cool for a couple of reasons that I'll talk about later. But first, we will kind of go through like NEMS, what it is, why it matters, who cares, etc. So NEMS is short for the National Energy Modeling System, and it's this behemoth of a model developed by the U.S. 30 plus years ago to model the U.S. energy markets. And its primary use these days is to produce the EIA's annual energy outlook. And once that's released, universities, researchers, groups can run simulations using the same code, and groups such as ours often run simulations for Congress, for other departments, for the White House, to see the impact on the overall energy picture of large changes such as drastic shifts in technology, large jumps in the price of oil and gas, or the least likely of them all, legislative action. And NEMS is particularly suited for this because it's able to incorporate supply, demand, and market activities simultaneously via the use of modules. Like you can see on your left, that's a schematic of NEMS. On the left side are supply activities, on the right side are demand activities, and in the middle are market activities and glue. But what you don't see there is a climate change module or an environmental impact module, just because at its core this doesn't really care about that. This is a purely economic model, so you're talking supply and demand. That's not to say that climate change doesn't come into effect here, because it's pretty easy to imagine how adverse climate change could affect supply or demand of specific fuels or like oil and gas. But what you do see is the oil and gas supply module, shortened to OXM. That's where I was working a little bit, and that encompasses all production methods of oil and gas for the onshore U.S., the offshore U.S., and Alaska. And when I say we're talking all production techniques, we're also including investment, profitability, innovation, all these things that all play a part. And within OXM is OLOGS, yet another acronym, which stands for the Onshore Lower 48 Oil and Gas Supply Submodule. And that's where I was working, and that is restricted to the contiguous U.S. And OLOGS is pretty sophisticated because what it does, it forecasts technically recoverable oil and gas, and then you take pricing data from other modules and technology data from other modules, and then you go from technically recoverable to economically recoverable, and as you work your way back up the NEMS pipeline, you can end up with probabilities that a specific group of wells will be developed in the future and the degree to which that'll happen. So now that we have that, what exactly was I doing? So OLOGS, I said, forecast oil and gas for a specific region, and I was trying to convert that to forecast oil and gas for a specific oil reservoir as defined by the USGS, like the U.S. Geological Survey. And that involved taking the code, adapting it, cleaning it, and chasing down variables to the ends of the NEMS Earth. But yeah. And how we do this, we did it using type curves. And type curves, in theory, from what I understand, are plotted solutions to a flow equation. And what this shows, this is a type curve for water flooding, and what this shows is that the first 3 years you pump water into an oil reservoir, you shouldn't expect anything in return, but in year 3 you start producing oil to the tune of 40 million barrels a year, tapering down until year 10. And right. And when I say we use type curves as a basis, I'm just saying that the numbers that go in the equations and the steps that go into making a type curve are what form the backbone of my model and program. This is model documentation. This just shows all the steps and some of the variables in the top left corner. The variables are interesting because we have input variables, which I, as I guess, commander-in-chief of this thing, put into the model in order to get out some outputs. And on like the highest level, given the similarities between oil and gas recovery methods, you have porosity as relevant in both cases. But even in cases where the variables aren't the same, you have analogous ones like API gravity and gas gravity, which are just measures of density relative to other types of oil and gas. I didn't have oil in place up there, but oil in place is a variable, gas in place is a variable. Those are analogous. And then oil and gas saturation as well. And while the input variables are pretty diverse, the output ones are not. We're looking for technically recoverable oil and gas. And then as you get more information, you can talk production for oil and gas, and then water and CO2 when it's relevant. You can do this for a single year, or for 5 or 10, up to 35, depending on your goals or what you need. I think one of the most nifty parts of this model is that you have a bunch of different recovery methods, technology types, and for each of these you have a different case with its own set of steps, kind of like before with the water flooding and equations. And all the variables have their own sensitivities depending on the technology type, which is just to say that your flooding rate doesn't matter necessarily when you're doing primary oil recovery, but it does when you're water flooding or CO2 flooding, and it matters to a different degree within each of those methods. So there's that. This is a results page, and if you can't tell, it's a page of errors. And this is up here for 2 reasons. One, this is by far the thing I saw the most over the summer. This program was written in Fortran, a language I barely knew existed, let alone knew how to use beforehand. So it was a struggle getting to know it. There's some code tidbits in there that are left over from when people would interact with computers using punch cards. So it's not something I was necessarily prepared for. The second reason that it's up here is because getting it right doesn't show anything, so they had to give you something. But it does work. It does give, it's a fully operational model, and the next steps are to start sourcing data, writing documentation, and integrating interoperability with other modules to get pricing data and technology data to move forward. And some final thoughts. I said the project was pretty cool for me because I'm writing a thesis that works a lot with the enhanced oil and gas recovery methods that I was working with this summer, so it was good to get familiar with those. I also work a lot with the numbers from NEMS and from the Annual Energy Outlook, so it was nice to understand the work that goes into them and the assumptions behind them, so I know what to do with them when I get them. The benefits and limitations of small models. My model was tiny in comparison to the overall NEMS model, which was good because that makes it relatively quick and responsive. I can find and fix errors pretty quickly, and when I went to do a full run, it wouldn't take 4 days and $30,000 like it does for a full NEMS run. But the biggest limitation was that since it's so small and it's kind of cut away from the mothership, the project was really only as good as the variables I put in. And some of the issues we ran into was when you're converting regional data into reservoir data, who defines the reservoir, how do they define it, and what was a reservoir span across multiple regions or states. So, and we had old numbers from the USGS and numbers from industry, which, there's a lot of due diligence to be done there. The most important thing I learned had to do with model purpose and model integrity. So I was just doing a research project, which means there was no outside influence on my results. But a lot of these studies are commissioned, which means different parties have different interests in the results. And there's always a question to be asked as to whether you let the results stand for themselves or whether you tailor them or start telling a story with the numbers. And that's a choice each person has to make. But if you decide to go with the storytelling, how much is too much? And that goes to model integrity, just because we ran into a case earlier summer where someone had tinkered with a model so as to make the results more palatable to someone in the past. But they never removed their changes, so now when we were making runs, we had numbers that were pretty acceptable, but not really factually correct. And if we were to remove this kind of false constraint, you end up with numbers that kind of depict a painful truth that aren't really useful to make recommendations based off of, because people who are in the position to make changes aren't really interested in seeing those numbers. So that's something we have to deal with over the summer, kind of going throughout the models. I want to say thanks to my mentor, Jose, and his team. They were great, and it was fantastic to work with something like this. I want to thank everyone at NETL Pittsburgh for helping me settle in and find office supplies and things like that. I want to thank everyone who made the Mickey Lynn Fellowship possible, and I want to thank the other Pittsburgh interns. I didn't see them very often, but when I did, it definitely made my day. So with that, I will take questions. Or not. So close.
Hi, great presentation.
Thanks.
I actually think that what you're doing, trying to forecast smaller scale like reservoirs. I think that is a lot better for more accurate forecasting because there's so much differences between the reservoirs with respect to all those parameters you showed. So, like, how are they planning to implement that? Like, are they like in real forecasting, like using this? Because there's so many differences and there's so many reservoirs and like you said, how are they defining the reservoirs? Like, like how big are the reservoirs supposed to be? Like.
So for the question of how to define reservoirs, we're using, which is admittedly outdated data from the USGS from about 2007. But in terms of what we're going to do with the modeling, I didn't really say this in my presentation, but we're trying to get depletion rates for individual reservoirs and then try to recommend technologies.
So when you say reservoir, do you mean like Eagle Ford reservoir, like a whole formation? Or are you talking about in certain states? Like what do you?
It would be formation by formation ideally.
Okay.
But it's not something that we at NETL are necessarily in the business of identifying.
Okay. Thanks a lot.
Mm-hmm.
In the world of reservoirs and deposits, is it a common belief that all of them have been discovered? Is there a belief that there's likely reservoirs that are not identified or discovered?
There is a large swath of undiscovered resources, but I think so. You have things that are split up into discovered and undiscovered, and then within discovered you have economically viable and those that aren't. So I would say that when you're doing current, like present day forecasting, you are only working with economically viable and technically recoverable discovered stuff right now. But then when you start forecasting in the future, you are making guesses about technology and assuming that a certain percentage of the ones that currently aren't discovered or economically viable will be in the future.
With the recent use of fracking, if you were to turn the clock back some years before fracking and do reservoir forecasting and so forth and so on, would those forecasts be significantly different than what they would be now, taking into account the ability to extract with fracking and other technology?
Yeah, I think particularly with fracking, you would have a much smaller role for natural gas, and you would have just oil playing a much larger part and much more subject to the fluctuations in price and things like that. But gas has had a pretty good steadying effect in that respect.
Okay.
Hi, my name is Zach Cesaro. I'm a junior at Cornell University studying chemical engineering. This summer I was in Morgantown under the mentorship of Todd Gardner, studying the synthesis and characterization of core shell nanoparticle catalysts, which are used for hydrocarbon reforming. So there were two main problems my project was hoping to address. The first is the flaring of natural gas. If you look at this satellite image, it's pretty small, sorry about that, but it shows the Bakken oil fields and Minneapolis in comparison to each other. And you can see that you can see the Bakken oil fields just as much as you can see Minneapolis, and that's due to flaring. So currently, during the extraction process of crude oil, we have a lot of extra natural gas that we can't really do anything with, and so we just flare it. And this happens on a global scale due to a lack of infrastructure and a lack of technology. And annual global flaring accounts for about 20% of the US natural gas demand, so it is a significant amount that we're flaring each year. The other issue that I'm addressing is the current natural gas reserves that are economically inaccessible, which George was just kind of hinting at. It's estimated that roughly half of the natural gas reserves are economically stranded. And so if you look at this graph, it kind of helps depict this. You have production volume on the y-axis and distance to market on the x-axis. So if you're close to the market, a pipeline for natural gas is economically feasible. And if you're producing a ton of natural gas, using cryogenic processes to turn that natural gas into a liquid and then ship it is also economically feasible. But if you're in the range of an average distance to market or an average production volume, right now there's no technology to economically get at that natural gas. And one possible solution to this is gas to liquid technology, which would allow you to produce a room temperature liquid form that you could ship for a cheap cost and therefore get at these reserves. So the gas to liquid process that I looked at utilizes a catalytic reformer which turns carbon dioxide and methane or natural gas into carbon monoxide and hydrogen gas, otherwise known as syngas. And then once you get this syngas, what you can do with it is turn it into diesel fuel or gasoline or a bunch of other fuels basically, which are liquid at room temperature, and then ship them wherever you need to go. The nanoparticles come into this because they are really small and therefore allow small active sites for this reaction to occur, which prevents the buildup of coke or carbon, which would otherwise clog this reformer and render the process useless. So I made 3 core shell nanoparticles. I used the polyol synthesis method, which is a common method in the field. I first synthesized these cores and then put a shell around them. And there were 3 different cores I used, but I used the same spinel shell on each of them. And then I went through and characterized these using a bunch of techniques, but today I'm going to focus on SEM, XRD, and microperformance reactor analysis. So starting off with SEM, I put these nanoparticles on a grid and then used SEM imaging, and what I got was what looks like the cover of an X-Men movie, but if you look really closely, you can see there are actually nanoparticles on there. They're larger nanoparticles. They're on the range of around 100 nanometers. And so to technically be a nanoparticle, you have to be 100 nanometers or less. So I knew while I was synthesizing them that I was producing on the upper end of this scale. But from these images, I was able to determine that I did make large core shell spherical nanoparticles, which is what I expected, so that was good. Next, X-ray diffraction. A couple people have talked about this in their presentations, but I used it to find 2 main things. The first was chemical composition of my samples, and the second was crystal size. So brief overview, you shoot X-rays at your sample, and the angle they bounce off at is determined by what material. So if you have nickel, it'll bounce off at 45 degrees, but if you have nickel oxide, it'll bounce off at 46. And you can tell these differences and use this to determine exactly what is in your sample. So these are my 3 catalysts and the shell, the XRDs of them. And if you look at the shell peak, you can actually follow this peak throughout all 3 catalysts. And so that showed me that I did have shell material in each of them. And then I went through and labeled each of the peaks and found that I also had core in each of them. So in conclusion, I found that all 3 catalysts were successfully synthesized with core and shell materials present. I then went through and made the shell by itself because the spinel versus oxide form of the shell isn't really well understood. So I calcined at 3 different temperatures. When calcined is basically just heating really hot to turn the hydroxides into oxides and to also have a solid state reaction between the oxides. So I found that from going from 450 to 900 degrees C, more of the peaks were spinel and less were just metal oxides, which is good. But at 900 degrees C, where my reaction occurs, you still don't have completely spinel, which is important to note. And then the second thing with XRD is size characterization, and you do this using something called the Scherer equation, which relates the thickness of the crystal to K, a constant, lambda, the wavelength of the X-ray, B, which is called full width at half mast. So if you look at this yellow peak that I analyzed in this example, if you go half the height, you measured the width right there. That's the B value, the full width at half max, and then just the angle it happens at, which is highlighted in the green arrow. This particular peak corresponds to a 77 nanometer crystal size, which is good because, again, that's about what I expected. I wanted larger crystals in the nanometer regime. Finally, I did a micro-performance reactor. Unfortunately, due to time constraints and high demand on the reactor, I was only able to do Catalyst 1, but I was able to run 3 tests on it. First a reduction, then the actual reaction, and then an oxidation. And from this, I was again able to get 3 main points of information depicted in these 3 graphs. The first of which shows the reduction process. So that's turning the core from a metal oxide into a metal. And so we expected, based on literature, for that to happen at around 300. But this peak showed that it started to happen around 500, which suggests that somehow the spinel must be affecting the core and the reactions that are occurring on it. The second graph is carbon dioxide production. So as we initially heated these catalysts up, they started to produce carbon dioxide, which suggests that just in ambient temperatures, carbon dioxide was attracted to these core shell nanoparticles, which is a good quality because we want carbon dioxide to react on the surface. So that was an important thing to note. And finally, the graph that really means the most out of all this is that it worked. It did change methane and carbon dioxide into carbon monoxide and hydrogen gas, which is good. It started happening at around 500 degrees C, and at 900 it was fully going and catalyzing the reaction. There is a lot of future work that needs to be done with these catalysts. We do need to test Catalyst 2 and 3 and see if they have the same performance or better performance than Catalyst 1. And we also need to test long-term performance because in the industry they want these catalysts to be in the reactor for a long period of time before you have to switch them out. We also need to test the effect of contaminants because in the industry, again, natural gas is going to have sulfur and other contaminants in it, and you need the catalyst to be able to deal with that. And finally, we want to vary the size. So these were, again, very large nanoparticles in the nanoparticle scale, and we'd probably want to try some smaller ones. I'd like to acknowledge my mentor, Todd, Jim, who helped me with SEM and XRD, Victor helped me with BET, Lydia for helping me out with XRD, and the Mickey Leland Energy Fellowship for this opportunity.
Hi. Okay, great presentation.
Thanks.
I just have a question. So I was doing something similar with some nanoparticles, and I was just wondering when you were testing them for their hydrocarbon reforming, how did you have them, like, were they in solution? Did you put them on a carbon support? Or they just as the solid?
So they're in a bed reactor, and what they're in is just quartz sand, which is just inert. They've been calcined at that point, so they're almost like a powder form.
Okay.
And so it's just a powder embedded in quartz sand.
Okay. And I just had another question. So from your SEMs, were you able to tell at all, like, the size of the shell versus the size of the nanoparticle?
No, and that would be something that we definitely would want to test in the future, because you could theoretically do an SEM before putting the shell on, so you could actually see the size of the core itself.
Because it's actually the nanoparticle itself that is doing the reaction, and so the shell's just to stop them from sticking
together, right. The
Okay.
core itself is where the reaction's occurring, and we know through BET analysis I didn't talk about that the shell has pores in it so that the gases can get to the core and react on the core. But again, yeah, we want this shell so that the cores don't stick together.
Okay, thank you.
Yep.
I know this wasn't the main focus of your research, but your object seemed to be to find a way to reduce the waste of this natural gas that's been flared.
Correct.
Did you run across any reason why it isn't being just re-injected for later in case technology would make it more likely to be economical to produce later?
As I understand it, in this extraction of crude oil, they're really just trying to do the most economic thing, and at that point, I think even injecting it would cost more, and so just burning it is the easiest thing to do.
Okay, thanks.
Thank you.